Hello geometry students, this is Mr. Fugay, and our video today is going to discuss the law of sines, specifically the ambiguous case, better known as side-side angle situations. So before we get into that, let's just go back to the first lesson and just talk a little bit about what we discussed in our first half. And that is the law of sines is a relationship that we've built that allows us to solve for missing sides and or angles in an oblique triangle. And just as a recap, an oblique triangle is a non-right triangle. So we look at two different scenarios, and the first half of the lesson discussed scenario number one. When we know two angle measures and any one side length, we learn that the law of sines is the preferred method for solving that particular triangle. But there is a second method, and we're going to discuss that in this video, and that's this one right here. When you know two side lengths and the measure of a non-included angle, we also can use the law of sines. The problem with this is that side-side angle is not information that can prove congruent triangles, or in other words, prove that we have a unique single triangle in the situation. So let's talk about what that situation entails specifically. So sometimes we are going to run into situations where we're going to be given two sides and a non-included angle. And there are going to be solutions in many situations for this, that we can solve the triangle. But we have to consider three scenarios. One scenario is that the triangle may not exist, so no solution. There may be exactly one solution. That would be our favorite, because that's kind of like what we did in the last lesson. But then there is a situation where we could have two unique solutions. So I'm not going to go over the rest of this page here where we're going to draw out each scenario. There is a video by the Algebros that I will link in the description that you can take a look at for a more detailed description of why this is happening. But for this video, I want to just bring you to this applet right here to show you. So here I have a triangle with a 30-degree angle, a measurement of 9, and a measurement of 4. This is by definition side-side non-included angle. So this is side-side angle. And notice this triangle cannot be created because this side that's 4 is not connecting to this dotted line. Now, if I make this A a little bit longer, okay, you will see what starts to happen, okay? So right now, let's just kind of hit it right there, okay? And actually, let's go make that 30 again if I can. I don't think it's going to let me. Well, that's okay. I'm not going to do it. Well, so the point is there can be one triangle in this situation for sure. There we go. There's our 30 that I was looking for. Because the reason I wanted to show you that is that here you can have it be an exact length, and so it would just be one unique triangle. That does happen. So we can have 0 triangles, 1 triangle, or 2 triangles. Now, you might not see this here. Let me play the animation. As this 5.6 swings, see how it touches that point and that point. So we can have this triangle right here that I'm tracing out, or we can have this much larger triangle that we're tracing out. So 0 solutions, 1 solution, or many solutions, or 2 solutions in that case. So let's talk about how we can determine that in some problems. So here is our first example problem. So it says determine the number of solutions and then when possible solve for the triangle. So let's draw out this picture here. So let's just draw a random triangle. And we'll go ahead and we'll label it ABC. And then let's label what we know. So we know that angle A is 63 degrees, side B, so that's going to be across from B, here's 18, and side A is 17. So notice that this is indeed going to be an SSA situation, so we were going to have to think about this could be an ambiguous case. So let's discuss why that is. So if I were to set up the law of sines here, let's go ahead and set up the sine of 63 over 17, that's sine of A over A, equals, and then we do not know angle B, so I'm going to say sine of B, but side B is 18. Let's go ahead and let's cross multiply this. So this is going to be 18 sine 63 equals 17 sine of B. Divide both sides by 17, and what we get here is 0.943. Now, when we get to this stage of the game, we are going to need to use our calculator. So we're going to use the inverse sine feature in our calculator. And in most of your calculators, that's the second sine button. Type in 0.943, and when you get an answer, you get a nice definitive 70.6 degrees. And you might say, okay, well, that looks like we have one solution. That's where we're wrong. Because remember that now that we have talked about the trig ratios in all of our quadrants, that sine is actually positive in 2 different quadrants. quadrant 1 and quadrant 2. So the quadrant 2 answer is going to be an angle that is located between 90 and 180 and is 70.6 degrees away from 180, aka the reference angle. And so when I do that, we actually get an answer of 109.4 also. This is telling me that angle B could be either 70.6 or 109.4. So let's talk about what we're going to have to do now to figure this out. So we have triangle 1 and then we'll have triangle 2. So I'm going to write out the information we have and see if we can finish solving this. So let's go ahead and let's write out ABC and then ABC, and we'll do the same thing here for triangle 2. All right. Now let's fill in everything that we know currently, and then we're going to begin to solve each of these as if there are two solutions, because we technically at this moment do. All right, the triangle in common, they both have a 63-degree angle from the given. We know that side A is 17 in both situations. And lastly, we know that side B is 18 in both situations. So that's a given. Now, in one of my scenarios, we're going to say that angle B is 70.6 degrees, and in the other situation, we know it's 109.4 degrees. Okay, wonderful. So what we can do now is we're going to begin to use the law of sines to solve the rest of these. So let's focus on triangle number 1 first. Angle C, using the triangle sum theorem, is going to be 46.4 degrees, which now will give me the power to solve for side C. So what I'm going to do to set this up is we're going to say sine of 46.4, sine of angle C, over C equals the sine of 63 over 17. And once again, we're going to cross multiply this. So let's write that out, sine of 46.4. And then lastly, we divide both sides by the sine of 63. And so side C here is going to equal 13.8. So we found that and we've solved this entire triangle. Now you might be asking, is this one or two solutions, Mr. Fugay? Right now it appears we have two solutions. We will run into the problem. You will glaringly see when it's going to be 1 or 0 solutions as we work through these. So let's go ahead to triangle 2, and this will confirm that we're going to have two solutions, because when I use the triangle sum theorem, I get 7.6 degrees. And just like we did in the last problem, I'm going to go ahead and set up another law of sines, which is going to allow me to solve for side C. So let's write those things out. We cross multiply and then divide by sine 63. And it looks like here our answer is going to be 2.5. So what we will gather from doing this first question is that there were two triangles that end up being able to be created from this situation. And that's because we had to consider a quadrant 1 and a quadrant 2 variance to the solution. But that will not always happen, as we're going to see in our next example. So let's do our next example. So once again, we're going to set up and just draw kind of a generic triangle here. So let's draw that out. A, B, C. Angle A is 112. Side A is 32. And side C is 20. So our initial law of sine setup would be to sine 112 over 32 equals, and then let's do sine of C over 20. And just like we did in the first example, we're going to go ahead and cross multiply. We're going to divide by 32. And we get that oops, I wrote that backwards, sorry. 0.579, that's what this is in my calculator, equals sine of C. We're going to use the inverse sine feature in our calculator, and we will see that angle C here is going to be equal to 35.4 degrees. And if we look at that as a quadrant 2 answer, so looking in quadrant 2, an angle that is 35.4 degrees away from 180, the other angle we would have is 144.6. So far, this seems like we're going to have two solutions again. And so let's go ahead and begin the same organization that we set up in the last problem. So we're going to have triangle 1, and then we're going to have triangle 2. Let's start with triangle 1. So let's write out our structure here. I like to write out all the givens, and then we'll start to solve these things in just a moment. So angle B, angle C, A, B, C. All right, so what do we know? Well, we know that angle A is 112. We know that side A is 32. And we know that side C is 20. We just solved in scenario 1 that angle C would be 35.4. So we have B and B to solve for in just a moment. Going over to our second scenario, we're going to still fill in the 112 that we know. We're still going to fill in the 32. We're still going to fill in the 20, and then angle C in the other scenario we got was 144.6. So when we use the triangle sum theorem, in the orange scenario, triangle 1, we get that angle B is 32.6. So that looks like to me that we can now set up a law of sines to solve for this. And so what does that look like? Well, it'll be sine of 32.6 over B equals sine of 112 over 32. And just as we've been doing with all of these, and you'll see that it really is a repetitive nature of solving, we cross multiply, we divide, and we see here that side B is going to be 18.6. So we got definitive answers here for triangle number 1. But when we go over to triangle number 2, look at what happens here. We have a 112 degree angle and we have a 144 degree angle. Well, if you know anything about triangles, triangles have to add up to 180. And if I add 112 to 144.6, that is going to give me 256.6 degrees, or we have two obtuse angles, which means that angle B is not possible because it would fail the triangle sum theorem. And this is a place where you're going to be able to see that not all of these triangles will have two solutions. So in this case, triangle number 2 is not possible, and the only triangle that we're going to end up having here is the first triangle, triangle number 1. So I want you to take a look real quickly before you try some of these about what happens here. Notice the process is very similar in the beginning, and you always assume there are going to be two solutions. And you only start eliminating them as you run into problems. So in example 1, we ran into no problems, which means we had two triangles. In the second example, we ran into a problem because the triangle sum theorem failed for the second triangle. Therefore, there was only one unique solution to this problem. So now it is your opportunity to try some of these out. So what I would like you to do now is to pause this video and try both of the you try problems here. Now, I'll go over the first one and then I'll have another pause for the break. So if you want to just try the first one and then press play, go ahead, but then I will talk about the second one as well. All right, here's our opportunity to check the first you try problem. So we went ahead, I created the triangle, labeled all of my information, and I set up my initial law of sines to solve for the first angle. Remember, we got 62.1 degrees when I put it in my calculator, but we must consider the quadrant 2 answer as well, which is always just going to be 180 minus the reference angle or the first angle that we found. So in this case, 180 minus 62.1. So my two scenarios are 62.1 and 117.9. So you will see over here on my triangle setup, there they are, and I'll also have my given information. Here's the rest of my work. So once I looked at both triangle scenario, I had to solve for side A, and I had my law of sines work down here. And then over here in my second example, I had to solve for side A as well, and here's my work for that. Remember, we had to use the triangle sum theorem to figure out what angle A was, and because both of them came out to be a positive number, we're good to go. The triangle sum theorem worked for that. Now, here's your next opportunity after this problem, is I want you to try this very last problem. So go ahead and pause the video if you haven't done it already, and let's give it a shot. Did anything strange happen? Did anything weird happen with this problem? Remember in the beginning of the video, I said there were 3 scenarios. One unique solution, 2 unique solutions, and we've seen examples of those. But what was the one that we haven't seen so far? Well, that was the other one. No solution. And I want you to take a look here at what happens with this. So we set up our triangle. We set up our law of sines, just like we've been doing. We cross multiply, create our equation, divide, and we get 1.125 for sine B. But if you put that in your calculator, you should have gotten an error. And that's because the sine ratio is not allowed to be bigger than 1. So this is a red flag, which means we're not going to get a solution, which means this triangle cannot exist. It is impossible for it to exist. Therefore, there is no solution to the problem. And that's what we're going to wrap up. Thank you for watching, guys.